Questions 11 through 20 on the 2019 Grade 10 AMC 10A. How many positive integer divisors of 201 to the power of 9 are perfect squares or perfect cubes or both? 201 to the power of 9 can be broken down to 3 times 67, all to the power of 9. Both of these are prime numbers. 3 to the power of 9, 67 to the power of 9 is what you would get when you assign the exponent to each prime number. Okay, so this is what we have to work with. Well, let's first look at the perfect squares, and then we'll talk about the perfect cubes. Perfect squares, the exponent has to be even, right? So 3 to the power of 0, 3 to the power of 2, 3 to the power of 4, 3 to the power of 6, 3 to the power of 8. Those are my choices. And the same choices hold true for 67 in terms of the exponents. 0, 2, 4, 6, and 8. So I've got 5 choices here for the exponent of 3, and I've got 5 choices here for the exponent for 67. So 5 times 5 is the total number of combinations, so that's 25. 25 perfect squares can be made. Now let's talk about perfect cubes. The exponent this time has to be a multiple of 3. So 0, 3, 6, or 9. And the same exponents would be for 67. 0, 3, 6, and 9. So here we got 4 and 4. So the combinations, there'd be 4 times 4, which is 16 combinations. Okay, so it looks like we have 25 and 16, which is 41, and that is one of the answer choices. But we've overcounted here. Overcounted by not too many. There's a few that are both perfect cubes and perfect squares, so we have to take that out. We've double counted those, so we have to take out that from the overcount. Which ones are those, by the way? Anything that's a multiple of 6, because 6 is a multiple of 2 and a multiple of 3. So those ones are 3, 0, 3, 6, and then 67 to the power of 0 and 67 to the power of 6. There's 2 here, there's 2 here, so the total combinations are 4. And therefore, this is what we overcounted by. So our grand total really is the 25 down here plus the 16 here. Subtract this 4 that we overcounted by, and therefore that is 37, which is the answer. Number 11, therefore, is C. Melanie computes the mean, median, and mode of 365 values that are the dates in the months of 2019. Thus, her data consists of 12 1s, 12 2s, 12 28s, 11 29s, 11 30s, 7 31s. Let D be the median of the modes. Which of the following statements is true? Well, the mean you can probably easily calculate. 12 times 1, 12 times 2, all that stuff, all the way up until we're going up to 28, right? Because all of them have 12. And then 11 times 29 plus 11 times 30 plus 7 times 30. And then, of course, divide by 365. And when you do all that math, you get it a little bit less than 16, about 15.7. And then the median is what we need to look at next. The median, of course, is the middle value. So there's 365 values. So the median of that would be halfway of 365, which is between the 182nd and the 183rd. Well, if you look at this carefully, there's 12 1s, there's 12 2s, there's 12 3s, and so on, right? So by the time you get up to 15, you will have 12 times 15 numbers, because there was 12 1s, then 12 2s, then 12 3s, and so on up until you got to 12 15. So each of those had 12. Each of those first 15 numbers had 12. And then this is actually 180. So the 180th number is a 15. And then therefore the 181, 182, and so on would be 16s. So therefore the median is the average of those two, and that's obviously 16. So we got the mean as 15.7, and we got the median to be 16. Now we have to look at the next thing, which is the mode, or actually in particular D, which is the median of the modes. Well, the modes, first of all, are the ones that appear the most, and there's a tie. 1, 2, 3, all those numbers up until 28 all appear 12 times, so there's a tie there. So these are the modes. There's 28 modes. So we want the median of that. Okay, the median of that would be the middle value, which is going to be the average of the 14th and the 15th value. The 14th value is 14, and the 15th value is 15. So the average of that is 14.5. So this represents my D. This what they talk about in the question stem. Okay, so now I have to rank the mean, median, and mode, and to me it looks like 14.5 obviously is less than 15.7, which is less than 16. So D is less than the mean, which is less than the median. So that, in terms of the answer choices for number 12, is E. Let triangle ABC be an isosceles triangle with BC equal AC and ACB is 40 degrees. Construct the circle with diameter BC and let D and E be the other intersection points of the circle with sides AB and AC, respectively. Let F be the intersection of the diagonals of the quadrilateral BCDE. What is the degree measure of BFC? Let us draw a diagram and see what happens. And let's label this now. So we've got A, B, and C. And we have also that BC is equal to AC. So BC and AC are going to be pretty much the same, making this isosceles triangle. And then we have the diameter BC, that obviously right here, that's the diameter of the circle. And then D and E be the other intersection points of the circle with sides AC and AB, respectively. So this is D right here, and this is E right here. And then F is the intersection of the diagonals of the quadrilateral BCDE. So BCDE form a quadrilateral, so I guess we can join D to E like that to make it a quadrilateral. And then the diagonals, let's put those in like that and like that. And where they meet is F. And they want us to figure out the angle BFC, so this angle right here. Okay, so this is basically what you call angle chasing, and we use a lot of the fact that some of the angles of a triangle equal 180 and things like that. So ACB is where we start, so that's 40. ACB, this is right here, 40 degrees. Since it's isosceles, this and this equal the same, so let's just say that's x, and therefore this is x. So that means x plus 40 is equal to 180. So 2x is equal to 140, x is 70. All right, so I'll put 70 there. Now, we have to look at this from the perspective of a circle. This is the diameter, and as I'm sure you know, any angle that's drawn inside a semicircle is a right angle. So that means that this is a right angle right here. And similarly, this guy, since that's also part of a semicircle, is also 90. So that's 90 right there. So if this is 40 and this is 90, that means this angle right here we can calculate pretty easily. It would be 180 minus 90 minus 40, and that is 50. So this is 50 right here. Now this whole thing was x, which is 70, so that means this is 20. And in a very similar way, since this is 90 and this is 70, we can calculate that angle. And that angle would be 180 minus 90 minus 70, which is 20. So this is 20 right here. So I think we have everything. Now we just look at this triangle right here, and when you do, we have 20 plus 50 plus that angle BFC, and that's got to equal 180. So angle BFC is 180 minus 70, which is 110. So number 13, the answer is D. For a set of 4 distinct lines in a plane, there are exactly n distinct points that lie on 2 or more of these lines. What is the sum of all possible values of n? Okay, so we've got to look at how can I get 4 lines to intersect, yes or no? Well, there's several scenarios. The first is when they're all parallel. And if they're all parallel, the number of intersections, which the question is calling n, is 0. Okay, let's look at the next one. Can we get one intersection with 4 lines? And the answer is yes, if they all kind of have a common intersection point like that. If you draw it like that, you'll get 1. Can I get 2 as the intersection points? And if you fiddle around with this one, you'll find that there's really no way of getting 2, exactly 2. There's 2, but where do I put my third line? If I put my third line here, I get 4. If I put my third line here, I get 3. If I put my third line here, I get 1, 2, 3. If I put my third line here, I get 4. So there's no way of getting 2. So 2, not possible. And that's, I guess, the key to the question right there. The next ones I think are pretty straightforward. You can get 3. I actually probably just showed you that one. How do you get 3? Here's 1, 2, and there's 3. 1, 2, 3. There's a way of drawing 3. And then we can, of course, draw 4. 4, I think I just did. 4 is pretty straightforward. Here's 4. 5. 5 we can get if we have this kind of a scenario. 1, 2, 3, 4, 5. And 6, where everything kind of crosses each other. Let's see here. Something like, that's 3 already. And then if I do that, that'll be 6, right? 1, 2, 3, 4, 5, 6, yeah. So for n, I've got 4, 5, and 6. So I'm going to include this, 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 and this for my possible values of n. This one is not possible. So the sum of all the values of n is 1 plus 3 plus 4 plus 5 plus 6, and that is 19. So number 14, the answer is D. A sequence of numbers is defined recursively by a1 equals 1, a2 equals 3 over 7, and an is equal to an minus 2 times an minus 1 over 2an minus 2 minus an minus 1 for all n greater than or equal to 3. Then A 2019 can be written as P over Q. What is P plus Q? All right, so we got a little bit of math to do here. The first 2 they gave us, so we've got to figure out A3 and so on. And as always with these kinds of questions, your hope is that eventually you'll see some sort of a pattern, and then you can extrapolate that pattern until 2019. All right, so here we go. Let's figure out A3. And remember, we're just using that formula right there, no tricks. That's going to be A1 times A2 over 2 times A1 minus A2. So that's going to be, in our case here, 1 times 3 over 7 times over 2 times 1 minus 3 over 7. And when you do that math, you will get 3 over 11. Now we move to A4. So A4 would be A2 times A3 over 2 times A2 minus A3. Again, using that formula. So A4 is going to be, let's see here, 3 over 7 times 3 over 11 over 2 times 3 over 7 minus 3 over 11. And when you do this math, you crunch out the numbers, you will get 3 over 15. I'm going to leave it as 3 over 15. I'm not going to reduce it. for a reason, and that reason will become clear. So let's just keep our tally here, 3 over 11, 3 over 15. Some of you might be able to see a pattern already, but in case you don't, no problem. I'll just keep going, a couple more. A5. A5, of course, will be A3 times A4 over 2 times A3 minus A4. So that's going to be 3 over 11 times 3 over 15 over 2 times 3 over 11 minus A4, which is 3 over 15. And if you crunch out these numbers, you will get 3 over 19. So I think the pattern is pretty evident. And A6 I'll let you do, since it's so much fun. And that comes out to 3 over 23. Okay, so I think at this point you can figure out a pattern. As you can clearly see, every one of these, if you don't reduce it, is a 3 on the numerator, but the denominator seems to be going up by 4. You see that? It's 7, then 11, then 15, then 19, then 23, like that. So we have to come up with a general pattern, and this is something that takes a little bit of practice, but it's going to be, in this case, 7, and then some multiple of 4. And that multiple of 4 in this case is n minus 2. And this is something that you have to figure out on your own. You have to look at this, and it's actually fairly straightforward. I don't want to make this too complicated, but it has to do with an arithmetic sequence. In our case, it was 7, 11, 15, 19, 23, right? So the general term is a plus n minus 1 d. And where a is the first term, and this is 7, and d is the common difference, which is 4. But the reason it's n minus 2 is because this is the first term, but this is 2. This is the second term, but this is 3. So you have to adjust for that, and that's why it becomes n minus 2. Like that. So, okay, so this is what an is, and what do we have to figure out? A 2019. Okay, no problem. Now that we have a formula, we can just sub in 2019 for the power of n, for the value of n. So when we do, we get 2017 when you subtract 2. So that's 3 over 4 times 2017 is going to be 68 plus 7, 75. So 8075. So this is my P over Q that they keep talking about. This is P over Q. And they want me to find P plus Q. Well, that's 3 plus 8075. And that is 8078. 8078. The answer is E. The figure below shows 13 circles of radii 1 within a larger circle. All the intersections occur at points of tangency. What is the area of the region shaded in the figure inside the larger circle but outside all of the circles of radius 1? I'll draw a couple diagrams here, or a couple lines I should say, and hopefully those lines will help. The first is a top to bottom one, like that. And then I'm going to draw lines that actually just go to the center, like this, like that, and then connect that one. So that's going to make a nice triangle, right? Okay. So at this point, let's first figure out a general formula for the area of the shaded region. Area of the shaded region is basically the full area, which is pi r squared, big R, minus 13 of those little ones, so pi small r squared. But small r is just 1, so I can just put that in there. So this is pi r squared minus just 13 pi. The only thing we don't know is the value of big R, which is the radius of the big circle. And that is what this diagram hopefully will help me. This side right here, if I count the radii, 1, 2, 3, 4, 5, 6. So that side has a length of 6. And similarly, the other sides have lengths of 6 because it's equilateral. And because it's equilateral, we know that this will be, if I draw the line down the middle, this will be 60, this will be 90, and then therefore this is 30. So I can use the 30, 60, 90 triangle to get that length. And that length from there to there, I'll just call it h for now. H over 6 is the same as root 3 over 2. So that means h is equal to 6 root 3 over 2. So h is 3 root 3. Now, to figure out the radius of the large circle, I just have to draw in a couple lines to illustrate something called the centroid. And drawn properly, it should match exactly. And the centroid basically is right here, this point right there. And there's a general rule, of course, that some of you may know, that says that if you have a centroid, it cuts that into a 2-to-1 ratio. So this is 2 to 1. So since the whole thing is 3 root 3, from here to here would be 2 root 3, and from here to here would be root 3. Because it's got to be a 2-to-1 ratio. So this part is 2 root 3. 2/3 of this, basically. And then from here to here is just 1, since the radii of the small circle. So the big R is that 2 root 3 plus 1. So now I can figure out this fairly easily. It will be pi times 2 root 3 plus 1 all squared minus 13 pi. So that looks like I can factor out a pi, and that's going to give me what? 2 root 3 times 4 times 3, 12, plus 4 root 3 plus 1 minus 13. And that looks like, oh, the 13s cancel, so I'm just got 4 root 3 pi. Yeah, that's it. So that's choice A for number 16. A child builds towers using identically shaped cubes of different colors. How many different towers with height of 8 can a child build with 2 red, 3 blue, and 4 green cubes? 1 cube will be left out. All right, let's give a very simple example. Let's say there was 3 cubes. There was 2 red, and there was 1 blue. And I want you to build a tower with 3 cubes. Okay, well, I can do that fairly straightforward way, I think. And it would be as follows. I'd have either red, red, blue. I'd have blue, red, red. Or I'd have blue, red, red like that. Those would be the only ways of doing it. Now, they've got, of course, a little bit larger of a question here. So how do we do that? Well, I've got 8 cubes. So I'll draw 8 spaces here, 1 for each cube. And for the first cube, I've got 9 possible choices, right? There's 2, 3, and 4. So there's 9 cubes altogether that I can choose from. So I've got 9 choices for the first of those 8 cubes in the tower. Then 8 choices for the second cube, 7 choices for the third cube, and then so on, right? You've done these kinds of questions before. And then, of course, you have to multiply them all like that. So this really is the equivalent of 9 factorial. Even though there's no 1 at the end, it still is 9 factorial. And this would be the answer if there was no doubles, overcounts. If there was all different colors, this would be the answer. But we have some colors, actually all of the colors, there's more than 1 cube. So what you have to do to account for the overcounts, you have to divide. So since there's 2 red cubes, you have to divide by 2 factorial. Since there's 3 blue cubes, you have to divide by 3 factorial. And since there are 4 green cubes, you have to divide by 4 factorial. That takes consideration of the overcounts and gives you a unique number. And when you do this math, you get 1260. And this is the number of unique towers that can be formed without all the doubles and triples and all that. So number 17, the answer is D. For some positive integer k, the repeating base k representation of the base 10 fraction 7 over 51 is 0.23 repeat to the base k, which equals 0.23, 23, 23, and so on base k. What is k? Well, I hope you're familiar with base k representations. I'll give you a very brief example. Let's say I have the number 173 to the base 11, and I said, what is this number? Well, it would be 1 times 11 to the power of 2 plus 7 times 11 to the power of 1 plus 3 times 11 to the power of 0, and whatever number that works out to. But I just wanted to illustrate how that's done. So keeping in mind now we have a different scenario here. We've got k's. So I'll just let x equal to this 0.23 repeat to the base k. Now, I want to expand this the way I did over here. But it's a little bit different because I've got the numbers after the decimal point. So it would be 2 times k to the negative 1 plus 3 times k to the negative 2. So that means this is 2 over k plus 3 over k squared. And that is x. Well, let's see if that helps me. I don't know. Now let's turn our attention to the expansion of this 0.23 repeat, 0.23 repeat to the base k. Now if it was base 10, we would multiply by 100 to bring these two before the decimal point. But we don't have base 10, we have base k. So we can't multiply by 10 squared, we have to multiply by k squared. So when you multiply by k squared, that's what allows you to bring 23 before the decimal point, like that. Okay, now what I'm going to do is just subtract those two. So I've got k squared x minus x, and then this would be 23.23 minus 0.23 repeat, and these are base k. So if I factor out an x here, I get k squared minus 1, and then this wipes out all of the decimal from both of them. So it just becomes 23 to the base k. Well, 23 to the base k is 2 times k to the power of 1 plus 3 times k to the power of 0. And this is the same. And this just becomes 2k plus 3. And then I'll bring that k squared minus 1 over, and that's x. And x, we know, is equal to this right here. But the question tells me that in base 10 it's equal to 7 over 51. So this, in base k, is this, but in base 10 is 7 over 51. So I can put that 7 over 51 here. And that will allow me to solve for k. So there we go. So cross multiply and get 7k squared minus 1 is equal to 102k plus 153. Put everything on one side and get 7k squared. This should be 7. Minus 102k minus 160 is equal to 0. And I think this should factor 7k, k, 10 and 16 plus negative. So that means k is either 16 or negative 10 over 7. And obviously the answer would be 16. So number 18, that is D. What is the least possible value of x plus 1 times x plus 2 times x plus 3 times x plus 4 plus 2019, where x is a real number? What I'm going to do is rearrange these just a little bit, x plus 4, and then I'm going to put the other two together, x plus 2, x plus 3. And when you rearrange them a little bit and expand them, this one and this one, you get x squared plus 5x plus 4, and then x squared plus 5x plus 6. Now these are very similar, so I think I might be able to manipulate them. X squared plus 5x plus plus 5 minus 1. And then this guy over here, x squared plus 5x plus 5 plus 1. And then plus 2019. So I think I got something very, very helpful. Now if I expand that, I get x squared plus 5x plus 5 squared. And then the second and third terms will cancel. Then you get minus 1 plus 2019. Now this x squared plus 5x plus 5 squared plus 2018 is what we have boiled it down to. Now I think it's a little bit easier. This, because it's squared here, is always going to be positive. Or it could be 0. And this obviously is just 2018. So we want the least possible value of this whole thing. The least possible value of that whole thing occurs when this is equal to 0. And when it is, that whole expression will be equal to 2018. So number 19, the answer is B. The numbers 1, 2, up until 9 are randomly placed into 9 squares of a 3 by 3 grid. Each square gets one number, and each of the numbers is used once. What is the probability that the sum of the numbers in each row and each column is odd? All right, well, 3 numbers are going to be odd if what? What is the scenario? I have to first figure that out, because I'm going to treat this, forget about the numbers. I'm just going to look at it as odd and even. That's the only thing I'm going to look at. Well, 3 numbers can have these types of scenarios, even, odd, even, odd, or odd, odd. The only time that the sum is odd is here and here. These will give even. So I'm really just interested in this scenario and this scenario to fill my square. So what I'm going to do is just going to draw one square and sort of show you how that would work, and then we'll try to figure out how many other ways are there of doing that. So here we go. I want odd, 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 and even, odd. Well, how many numbers are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. These ones are even, so there's 4 even, and therefore the other 1, 2, 3, 4, 5 are odd. So I've got to put 4 even and 5 odd in this grid. Okay, one way of doing that is doing odd, 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 and then even, even. That's one way. Another way would be odd, 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 and then just kind of move the, I guess, 3 in a row column to the right a little bit. Another way is to do it like this, and then you get the evens there. So that takes care of all the ones where the odd, odd, odd was the top row. How about we make it the middle row, and then we sort of do the same kind of thing. There's 1, and then let's move that. There's 2, and then we're doing it for the middle, right? So move it there, and that's another one. And then the last one would be when the odd, odd, odd is the bottom row. So that's this kind of scenario. And then again, we can make very quickly the different scenarios. Here's one more, and last one, odd, 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 odd. There we go. So these, I got 9, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 9. So my probability is 9 over something. Now what's my something? Well, the denominator in a probability question is always the total number of ways. The total number of ways, without regard to any rules, is from the 9 numbers, you want to choose 5 for the odd, and from the remaining 4, even, you choose all of them. So this is basically the answer. So 9 choose 5 is 120. It's basically 9 factorial over 4 factorial over 5 factorial, which is 126. And there you go. That's the answer. And of course, they're going to lower it to lowest terms, which would be 1 over 14. So number 20, the answer is B.